Welcome to today's webcast series presentation, Creating and Maintaining FE Mesh for Structural Designs. There's a Better Way. My name is Bob Drake, editor of Civil and Structural Engineer magazine, published by SCIA Group. Thank you for joining this webcast, which is sponsored by SCIA. Before we begin today's presentation, first some general information about the webcast and the webcast platform. The views of the speakers and organizations participating in this webcast are their own and do not necessarily reflect those of Civil and Structural Engineer or its publisher, SCIA Group. If you have any technical difficulties while viewing this webcast, please submit questions or a brief explanation of your technical problem using the Ask a Question box on the left side of the webcast dashboard, and a representative will assist you. Note the button in the upper right corner to enlarge the slide viewing window if desired. During the webcast, you also can submit questions to our speakers using the same Ask a Question box. Submit your questions at any time, and we will try to answer as many as we can later in the webcast. SCIA Group encourages group learning for our events. If you are viewing the live webcast with a group on one registered person's computer, that person must complete and submit the multiple viewer registration form for the group in order for everyone to earn credit. Download the multiple viewer registration form from the event resources on the left side of the webcast dashboard. Submission instructions are on the form. Also note a link in the event resources section to download a PDF of the slides in today's webcast. Details on downloading a certificate of completion will be provided later in the webcast. Viewers of archived webcast must pass a quiz in order to download a certificate of completion. Additionally, at the end of today's event, we will provide a webcast evaluation survey for you to submit your feedback. Today's presenter is Ben Follett, U.S. Product and Marketing Manager for SCIA, where he helps engineering firms streamline and integrate their 3D engineering workflows. Prior to his work in the software industry, he was a structural associate with an international engineering consulting firm. So for today's webcast, Ben will be sharing his computer screen to provide some live demos. So let's get started. Ben, I'll hand it over to you.
Thanks very much, Bob. Okay, while we wait a second for my screen to kind of publish here. Thanks to Bob for kind of the introduction. And so today we are going to talk about mainly about meshing in SCIA Engineer. And so as you can see here, I want to start with some learning objectives. And so we're going to learn about four main things in terms of finite element mesh and mesh in our software SCIA Engineer. The first is just kind of the basic mesh setup and automatic generation based on some global settings. Next, on how to apply various local mesh refinement options, including at nodes, edges, and entire surfaces. Thirdly, we're going to look at automatic mesh refinement based on applied load to the structure so that we can create an accurate and error-free mesh and use the power of the software to do that. And then finally, we'll look at some results-based tools such as averaging and integration strips that we use to fine-tune the results from the finite element mesh. So before we get into SCIA, let's talk a little bit about the basics of finite element analysis. So for those who maybe are new to this type of analysis, basically what we're talking about is a numerical technique for finding solutions to partial differential equations within a specific set of boundary conditions. And so really what we have is a large problem, and in many cases large structures or something that you would never attempt to do by hand, that is subdivided into smaller pieces, which we call then finite elements. So each finite element includes a subset of equations relative to the original larger problem. So this set of equations for each element is then recombined into a global system of equations for the final calculation. And a lot of this happens in matrices and matrix techniques. So some of the advantages of this finite element method include an accurate representation of complex geometries, the ability to easily represent a large global solution, and then also the ability to capture local effects in a much larger problem. And so in that case, you're not just concerned with maybe the global solution, but you can also concern yourself then with the local effects, which in a lot of cases we need to do as structural engineers. So let's jump right into our learning objectives. And so the first thing that I want to just discuss is the basics. Let's talk a little bit about the basics of SCIA Engineer, the software, and how you can utilize finite element mesh. Now we understand that meshing and in turn doing a finite element analysis is not always a requirement of projects. Many projects may be just frames or other things in which meshing isn't a requirement or really isn't needed. But in many cases what we find is that most of the projects or most of the users, the engineers that require this type of software spend a lot of time to either refine or to set up the mesh or to manually discretize the structure so that and that takes a lot of time and effort and can really extend the time frame of given projects. And so in this case, for the lay user, for the kind of the general setup, we require a few things. The first is to set an average size of any 2D element. And so this goes for all walls, all plates, all shells, so any 2 or actually 3D shell-based element in the software. The second is we have the option to define a mesh size for panels. Panels are a little different than the mesh that we use for plate or shell or wall elements. Panels are actually used to distribute load. They are another type of 2D element, but they don't have any stiffness. They're just used for that load application or the load distribution. And so we can also set the panel definition in that case. Finally, an elastic mesh is a type of mesh that we use by default, so that's a checkbox that's always on. And then we also have the option to set whether or not we want to use the automatic mesh refinement. And we'll look at this automatic mesh refinement in detail in a little bit later. Now, one of the other things that I didn't highlight but I wanted to mention is that there's a general mesh setting called average number of tiles on 1D element. For structures where maybe there are no 2D elements, SCIA still has the ability to mesh 1D elements, and this is mostly used for advanced nonlinear design or advanced nonlinear analysis or stability analysis when we're really trying to understand the buckled shape of maybe a frame or a set of frames. And so in that case, we can see really the internal effects between the I and the J nodes of a given 1D member. So the first thing that I'm going to do here is I'm just going to show a quick video, and this is a video just showing the mesh generation. And so I've got a model. I'm just going to go ahead and double-click on mesh generation here, and it's just going to generate the mesh for us. And so it generates and gives us some information about the number of nodes, the number of elements that are created in this particular model, and then it's going to show us that graphically. And so within the mesh generation, this we're not segmenting the mesh itself. We're not breaking the slab into a bunch of individual elements. What we actually have here is that the mesh is an attribute that's applied to the 2D member. And so the attribute in that case is used solely for the ability to look at and maintain and manage results that we have in the software. And so in this case, it's not like other softwares where you would automatically, as soon as you mesh, you lose the overall geometry of this slab in this case, but you have the ability to continue, make changes, change the geometry, and continue to just regenerate the mesh. It's also possible to generate the mesh automatically during the calculation. And so really you can run the mesh generation before the analysis so that you can verify it and validate it and maybe use some mesh refinement. Or if you don't really care and you just want to set a global mesh, when you run the analysis, the mesh will automatically be generated. So the first thing after we've generated our general mesh here, we want to talk a little bit about mesh refinement now. And this really is, I think, the biggest issue or the biggest problem that people run into when they are talking about how to manage and how to utilize information within a slab or a plate or a wall, is how to deal with the refinements, because a lot of times this can take a really long time. And a lot of it has to be manually done. So we do offer some local mesh refinements, which are more of a manual process, both at nodes, at a 2D member edge, and then also at a surface. And so all of these are possible. And so to talk about this a little bit, let's go ahead and switch now into SCIA Engineer. And so I'm going to do some different live demo throughout the presentation. And obviously, if you have questions on anything that I've done or if I've done anything too fast, please put your questions in the question chat box, and we'll try to answer some of those at the end. And so the first thing I'm going to do here is I'll just look in the mesh setup, and we have our 2-foot global mesh set. I'm going to go ahead and just click to generate the mesh. So I'm just going to run the mesh. It'll generate very quickly and give me some stats on the mesh that's been generated. Now within this mesh, we also have loads applied to this structure. So if I go into the load service here, I can see that one of the loads applied at this structure is a point load at a node within our top surface here. So the first thing I want to do, because I know and I understand that applying a point load at a very, in finite element space, when you apply it at a single node, is basically applying a load at a singular location. There's no distribution over a larger area or anything, and we'll talk about some ways to do that. But the first thing that we can actually do in this case is refine the mesh around that particular node. So I'm going to go ahead and select our local mesh refinement. And so, like we mentioned, there's 3 different types of local mesh refinement. The first we're going to use is that nodal mesh refinement. And so we can set a radius, so the radius around whatever point we're going to select, and then we select the ratio as compared to the global mesh. And so in this case, I'll set like an 1/8, and I'll go ahead and select that location there. And now this yellowish circle is just kind of a graphical view to let you know that you have a mesh refinement at that given point, just so you know what's going on. Now, before we go ahead and regenerate the mesh, let's go ahead and look at some of the other local mesh refinements and what they do. So the second one I'm going to add is a 2D member edge refinement. And so remember, we can select an edge, and then we select our mesh size. So in this case, we have a 2-foot global mesh. I'm going to set a 1/2 foot local mesh, and we'll use maybe that member edge there. And then finally, we can use an entire surface mesh refinement to change the size of the mesh. So again, I'm going to go ahead and select maybe a 1-foot size, and I can go ahead and select this entire front wall here. And so now with those mesh refinements set, I can go ahead and use the shortcut button up here to regenerate my mesh. And so remember, we had 2,200 roughly 2D elements. Now we have 3,000, and we can go ahead and see very clearly the mesh refinement that's happened. And so if we look at this, obviously we have a 2-foot mesh generally on the top and on all the other slabs, but we have our 1-foot mesh now here. We also have our line mesh refinement here of a 1/2 foot. And then finally our nodal mesh refinement of about an 1/8 of the 2-foot mesh. Now, one thing you'll notice is that anytime this meshing happens, there's a lot of intelligence that's built into kind of how the refinement happens and how things are connected. So obviously, it's not possible to go from a square 2-foot mesh just right down to an 1/8 of a foot mesh or something like that, right, or a 1/4 foot mesh. And so SCIA will have to do some smoothing, if you will, to get to to smooth out the mesh to get from a 2-foot mesh down to this much smaller mesh. And so all of that is done automatically. I didn't set any other criteria. I didn't set any other factors. I didn't have to change or manipulate anything, and that's one thing that you'll notice. The other thing that you'll notice is that SCIA by default will utilize rectangular, quadrilinear elements when it can. That's the easiest element for it to use with the 4 points in a center. Where it has to, it will use triangular elements, and so, or an element that is some skew of a 4-sided element. And so that's just kind of the default in how SCIA creates what it is creating. So let's go ahead and jump back into the PowerPoint here. And so the next kind of level of detail in this, the next level of kind of ability, if you will, is the ability to expand upon local mesh refinements and utilize automatic mesh refinement. And so we developed this using some error estimation techniques in conjunction with a consulting company and also the Czech Technical University in Prague. It's actually one of the universities that a lot of our developers and a lot of the people that work for our company where they also teach. And so this actually works by comparing calculated stress values with their theoretically calculated stress gradient values within the mesh. So a few of the things that the user defines, we're going to define a target mesh error percentage, and then we're going to define load cases for the refinement. So we can pick any load cases that we have in the model, and it's going to utilize the results of those load cases to figure out how the mesh needs to be refined. And so some of the results that are included, and we'll look at these in detail when we actually get into the software. The first is just a quality of global numerical solution. So basically it's a relative error percentage. The paper, and we'll talk a little bit about the papers that were written, makes a recommendation of 30%, that you want to be below 30%. And we'll see actually what that looks like graphically, what happens when we get below 30%. We also have the ability to look at a global mesh error, and a proposed mesh refinement. And we'll be able to see both of these graphically. So it's not very black box. It's really open and allows you to kind of see exactly what it's proposing, how it's getting to that that percentage, and so on and so forth. So let's go ahead again and jump back into SCIA Engineer. I'm going to switch my model here to just another model I have set up to do automatic mesh refinement. And so the first thing I'm going to do is I'm going to open up the mesh setup, and we're going to enable this automatic mesh refinement. So if I enable the mesh refinement, the first thing here we have is a target error percentage for that mesh. Right now it's set at a default value of 10%. Basically what this error percentage or this number means is that this is the maximum percentage that SCIA will look through when it's doing refinement and comparing results and displacements between two adjacent mesh elements. So if you have if we look here, if we have two rectilinear mesh elements, the percentage and the results between the two has to be below 10%. And so that's how it will propose its refinement. The next is our selected group of loads. And so in this case, we can choose to use whatever loads we want to use. I'm going to choose to add all of them. So I'm going to use the self-weight. I have some superimposed dead load and live load applied as surface loads. And then I have our point load that we applied here. All of those loads, we'll use them all to do a refinement. Now with that information set, I'm going to go ahead and click the mesh generation button. So this is just going to generate our 2-foot global mesh. So that's our 2-foot global mesh. It's the mesh that we set as our general solution. The next thing I'm going to do is I'm going to run the calculation. So I'm going to run the linear calculation in this case with the 2-foot global mesh and the settings of the automatic mesh refinement. So this will take just a second, and as soon as that finishes, the first thing that we'll notice here is that we have a result for that quality of numerical solution that we've discussed. And so we can see here that it's set at 40.36%. Now, if you remember, we had talked about good practice is to have a value that's below 30%. And so at this point, the software is essentially telling us that they would recommend, or the software would recommend, to use some refinement. Now, if I want to go ahead and look at or take the next steps in this refinement process, I'm going to open up the results service in SCIA. And I'm going to go ahead and open up 2D members. And now with the automatic mesh refinement enabled, we have a result called numerical error / mesh refinement. And so this is where we can see these results. Now, with any result in SCIA Engineer, when you select the result, the properties palette here is the kind of the driver for what type of result or how you want to view the result. Okay. And so if we go ahead now and say I want to view the, let's decide we'll view the numerical error. We can see a numerical error percentage. Now, where we have, very standard slab where there's nothing that's changing, where the load is very regular, we have the purple, right? Basically meaning there's no error percentage, the mesh is sufficient in that case. Where we see that mesh refinement is required is really where we have load applied, where the points of the columns connect to the slabs. All of these locations are where the system is saying, hey, we have a higher error percentage than we would like in this case. So with that, we can also go ahead and look at its proposed mesh refinement. So this is how it's proposing a mesh refinement. And you can see that it works in both directions. It's not just creating a finer mesh, but it's also going to create a coarser mesh where it can. And so in this case, it's actually creating on the 2D, on this wall here, saying, hey, we can go from 2 feet to 4 feet actually because we have very regular loading, we have very regular distribution of the forces, and we have no changes in the geometry. And so now with this, if we want to accept this proposed refinement, what we're going to do is we're going to go ahead, oops, sorry about that. If we're going to accept this proposed refinement, we're going to go ahead and click the mesh generation button. That mesh generation will take a second or two longer here because it's going to generate quite a bit more mesh elements. So remember we had 2,000, now we just created 16,000. And so we can see now, the mesh generation that was created. So based solely on the loads and the geometry that was created. Now, we lost our results because we changed the mesh, so let's go ahead and rerun the analysis. Now, again, this is going to take just a second longer because we have significantly more two-dimensional elements in this case, but it shouldn't take too much longer. Now, again, we're going to get presented with, the first thing we're going to get presented with is that quality of numerical solution. And so if we look at that quality of numerical solution as it pops up here, we should hopefully see something that is below 30%. So now our quality numerical solution is 28.61%. Now, this quality numerical solution is actually, it's just an equation. It's the energetic norm of estimated error divided by the energetic norm of displacements. And, we don't need to really go into depth what that means. I'll show you the paper, and the slides will include the links to these different papers which talk in detail about what all of this is and how all of this works. So now with this information, we can go back into the mesh refinement, and we can say, hey, let's go ahead and look at our numerical error. Now you can see that the majority of the numerical error graphically is showing as purple. Now this is a zero numerical error. So all of the refinement we did has really gone a long way to saying, hey, yeah, we have a sufficient mesh in this case. Now obviously if we zoom into a location where we have a node from a column connecting to the slab, we're always, no matter how far we refine, we're always going to have two adjacent mesh elements where there's a reversal of the load, right? And so in that case, we're always going to have, these kind of peaks, if you will. But for the majority of the structure, we can tell that we've got a good enough result. Now, if we wanted to, we could look at the mesh refinement again and see it would again propose something to go even further if we wanted to. But since we're below that 30%, we have no need to do that. So what are some of the advantages? Obviously, some of the advantages might have been kind of obvious, but what are some of the kind of what we deem to be the advantages of this automatic mesh refinement? So the first thing is I think it saves time while removing the guesswork of determining where refinement is required. Obviously with manual mesh refinement, sometimes it's very easy. We see a point load, we know we probably need to do a mesh refinement at that point load because we're going to get a really high peak in that slab or something like that at that location. That's obvious. But in some of the other cases, maybe even at just the connections of the slabs, to the columns, having to apply all those manual refinements just would take a while and it would take a lot of guesswork. Also, the refinements aren't just kind of based on some hocus pocus. They're all based on the model, the loading of the model, and the results of the model. And so based on the application that you have, you're going to get a very specific proposed mesh refinement and a very specific mesh refinement based on the information that you have in your model. So it's not that two models are going to get meshed and refined the same. It's really going to be specific to your model. I think it provides more precise results. So if you were doing a manual mesh refinement, you would probably have to make some guesses and take some shortcuts and not be able to get to a manual mesh or a refined mesh as kind of in depth as this. Also, it gives you the ability to utilize graphical results, making it easy to see where you have the largest error or you need the largest proposed refinement. And so it really kind of gives you an idea. And maybe it could even help you when you have issues with your model. Maybe you have a point load that you didn't expect to have there and it was creating a refinement. Kind of gives you a little bit of troubleshooting. And then finally, it's based on some established methods. So the superconvergent patch recovery theory is actually a very established finite element kind of method and method for doing these kind of refinements. And so that's what's being used kind of as the logic in the background to do this. Like I mentioned, we have these papers, and so these are actually links to 3 different papers, a paper on the superconvergence and the superconvergent patch theory, one about kind of adaptive mesh refinement and this patch theory, and then finally a very specific paper on error estimation and adaptivity in finite element analysis in SCIA Engineer. And so basically how those 2 papers were applied to do what we're doing now in SCIA Engineer. Now, one of the biggest things with mesh results of any type are how to use them in a real engineering application, right? So obviously we're not going to pull out results from these very small mesh elements to then use in design, right? So how do we use the results that we have from a finite element mesh, sometimes very detailed results, how do we use those from a finite element mesh in a way that we as engineers can use them in our designs, especially, and now SCIA does a lot of the design, can do all the concrete and steel design that you want, but in some cases a lot of engineers are pulling design results outside of analysis software and doing them either in spreadsheets or in other softwares because they can have a little bit more control. And so what SCIA does is SCIA offers some results tools. And so we'll talk about some averaging strips, integration strips, the ability to cut sections, the ability to look very specifically at detailed results in the mesh nodes. The other part of this, well, let's go ahead and look at that first. So let's go ahead and look at some of these results kind of related tools that we can use. So I'm going to jump back into SCIA again, and I'm going to switch again to another model. So the same model, we're going to use the same model throughout the whole process. But the first thing I'm going to do is I'm going to go ahead, I'm just going to select the top slab here, and I'm going to select for a force. We can go ahead and look at a specific force in the top of the slab. And so I selected here a shear force based on the fact that we're looking at that point load that we've applied to this node here. And I'm going to go ahead and refresh this particular output. So in this case, we have now kind of just an isobands or a contour plot of exactly what's happening here. Now, one thing that we can see here is that we've got some, some pretty regular loads, but if we zoom in here, we can see that we do have some peaks at that application, that location of point load application, right? And that's because exactly what we talked about. We haven't done, there's not really a refinement going on there, and we haven't done anything to kind of remedy the fact that we still have a load going through a very infinitely thin, infinitely small point. So what we can do in SCIA Engineer is I'm going to go ahead and open up what we call result tools. And the first result tool we're going to talk about is what we call an averaging strip. And so what an averaging strip does is it's going to allow us to define a geometry and then average the results of the finite element mesh based on a certain load over that geometry. And so if I double click on averaging strip, we can use a point or a strip width averaging strip. So I'm going to do it at a point. We're going to apply it at that point load location. And then we can set a size. So I'm going to make it basically 16 inches. And then we can choose how we want to do the averaging. We want to do it in one direction, in two directions. So in this case, I'm going to choose to do it in both directions because we have a concrete slab. It's a two-way concrete slab. It's going to be reinforced in both directions. And so we can go ahead and select to apply it. Go ahead and, first I have to select the slab. So let's select the slab here, and then we can go ahead and apply it there. So now effectively we have that averaging strip. So if I go back now to the internal force, we can go ahead and review again that same internal force. So this is the internal force that we had, right? So let's zoom in here. So somewhere on the order of 1.03 kips per foot and, probably between 0.6 and 0.9 kips per foot. Now within the result here, we can turn on this averaging of peak. So if we select that and then click to refresh the result, we've now averaged the peak there. So we've actually dropped now the result to say, okay, it's going to average based on that size. Now, if our mesh was a little larger in this case, or excuse me, a little bit coarser, smaller in this case, we get even better refinement or better results because this would have had individual mesh elements within that averaging strip. And so really in that case is all dependent on how you want to do an averaging compared to how you want to allow the mesh to be refined in that case. Now another option for looking at results is creating what we call an integration strip. So an integration strip is actually a strip that allows us to basically take forces within a slab, a 2D member, and integrate them over a defined width, effectively giving us 1D member or beam results. So in this case, I'm going to go ahead and set a constant symmetric width. So let's make it, 24 inches. And then we can go ahead and draw the slab or the integration strip on the slab here. So I'm going to draw it from this point over to this point. While I'm doing this, I'm going to go ahead and select this slab just so we can see only that slab, and I'm just going to kind of put everything else on in kind of a view that we can see it, but we can't select it. So now if I go ahead and if I want to look at the results for this integration strip, I choose a beam result. So I say internal forces on beams. And I can go ahead and say for maybe the live load, so there's a surface live load on this particular slab, I want to go ahead and look at a rib and integration strip result for moment. And so if I choose that now, and we can go ahead and change some of the viewing parameters of this so we can see this a little better. So let's turn on the units and the hatching. And we can now see kind of that moment diagram that's happening there. Maybe we even want to look at the extremes difference, so we can turn on these local extremes, right? So now we can see exactly what we're doing. So essentially what this is now is this is a slab result. So this slab is 6 inches thick. So this is now reporting us results as if we had a 6-inch deep by 24-inch wide beam. And so we can use these results to do strip design, or if we had a 1D member that we needed to look at, or so on and so forth. So we could use these results in a variety of different ways. So essentially we now have an equivalent beam in which we can look at moment and and shear and really whatever else we want. Now, one thing that I hadn't mentioned, any result that you have in SCIA, any result in this case, is available to look at in what we call the preview. Preview is always just kind of a table result of what you're doing here. So I'm looking at the wrong result here. So let's go ahead and switch back to our 2D member results. So let's go back to our internal forces in this case. Here we go. And we'll look at the table results here. So we can see this, we just have a table of the result that we're looking at. And so we can see the maximums, they correspond to the maximums that we have here. We can go ahead and use this, export this to Excel, export this into our engineering report, kind of whatever we want in that case. Now it's also possible to go ahead and look at and add sections on 2D member. So a section is very similar in how it can be used to an integration strip. The only real difference is going to be that the section can be cut in any direction, so we can cut it in any direction, so it can be drawn in any way, and it's only along that very defined line. So it's not integrating forces over a strip width or anything, it's just defining it at that particular section. Now it's also possible, when we look at any of these results, to review results at, so maybe we choose the displacement results, review results at individual finite element mesh nodes. So if I go ahead and look at, let's select this here, and we'll use, again, the live load. So we get our deflections here. So these are deflections of our slab in this case. Now I can choose to look at the detailed results in the mesh node. And so it's going to show me all the individual meshes, and I can go ahead and zoom in and say, hey, maybe we'll get something bigger over here. Say for this node, okay, for that finite element, that's element 14,000 and some, at a certain coordinate location. This is the results that are happening. This is the deflections that are happening. So based on self-weight, dead load, live load, point load, these are the deflections that are happening in that particular case in this direction. And so we can look very detailed at those results. It's also possible for us to go ahead and look at results not only on the mesh, or excuse me, not on the kind of a contour plot, but we can change the system to say, hey, maybe I want to look at edge results. So in this case, I'll turn off the standard results and I'll say, show me the edge results, right? So now I have edge results reported to me just based on, based on what we have in the system. So we can see all of those edge results. We can see where our maximum and minimum edge results are. Again, we can look at all of this information in a table. So let's go ahead and generate this. We can see all these different results, and we can do different things with them. Also, if we wanted to use a section, we can turn on the section here to show kind of different options for what we want to show. We could also include both at the same time. So if I have them all at the same time, we can see exactly kind of where these edge results come from, and they come from this particular slab. Now the last thing I want to talk about is, we've talked about meshing, the generation of that mesh. We've talked about the manual mesh refinement, the automatic mesh refinement. We've talked about taking some of these result tools and being able to look at the mesh results in different ways that allow you to do better design. But what about troubleshooting? That's one of the big things that always comes up in structural analysis software, finite element analysis software, and when we talk about meshing. So what happens when you've got a structure that's unstable, that fails, that just runs into issues? What can you do? What does SCIA offer you in that case? And so we offer a few troubleshooting tools. The main one is what we call the Singularity Check, and then we also offer just some selection tools to be able to find things and kind of manage and navigate what you're doing in your model. So one last time, I'm going to go ahead and jump into a different model here. And so very simple model, but in this case what I have here is I have a pin support on this L-shaped wall. I've got a surface force applied here, and then I've got this fixed wall here. And so the first thing I'm going to do is I'm just going to run the analysis. Let's just run the linear calculation. Now, immediately, it's telling me that something's wrong. Now, obviously, I've done this on purpose, but it's telling me that the stiffness matrix is singular, that for some reason the structure is found to be unstable. And so it's telling us where the structure is unstable at. So it's giving us some dimensions, it's giving us a direction, and it's giving us the slab itself, so in this case, slab S2. So if we click OK, it's then going to ask us if we want to do the singularity check on the model. So in this case, no, I don't want to do it, but it gives us a little bit more information about what the calculation happened and why the calculation was aborted. And so we could go ahead and, at this point, we could evaluate kind of maybe we didn't connect something properly or whatnot. Now, probably more importantly, if we would have run or allowed the system to run that singularity check, so we'll go ahead and do it this time, what we're going to see, what the singularity check will do, is it'll actually do a rigid body mode of the kind of the structure. So basically it's going to give us a deflected shape and an animation of this particular structure with the loads applied and how it's reacting. And so in this case, if we go ahead now and apply the animation, we can see here that even though it looks like maybe that this wall and this slab here are connected, they're really not. We really haven't created a connection in that particular location. We can see that this slab, because it's pinned and because it has a load on it, is just kind of rolling over. And so now we have a much better idea, rather than just seeing that, hey, you've got a singularity at this mesh node, or you've got a problem at this particular element. You can really see what you have to do in this case. So in this case, we know, hey, we've got to make a connection here. So if I go ahead and stop this, we can go ahead and look at, the side view to see, oh, wow, we have a, we never connected this. Maybe this was an issue in your modeling. Maybe you imported this model from Revit or something like that, and it was never connected properly. And so we could now make a change to say, okay, this is at a certain location. We could go ahead and select that element. I can select these nodes and say, hey, I want to select all of these nodes, and I'm going to go ahead and make sure that they truly do connect there, right? And so now if we go ahead and look at on the side view, they surely are connected. The other thing that we can do is that once we've generated our mesh, we can go ahead and use selection tools. So I can go ahead and select, a certain mesh node. So if I type in select MN, which is select mesh node, I can go ahead and then type in a specific node. So I think, we have a certain node, and it's going to find that node. So it's going to identify that node for me. So when it tells us that we have a failure somewhere, we can say, hey, I want to find the mesh. I want to find the mesh node that was associated with where that failure was. In this case, I just kind of picked one at random. And, we can kind of evaluate on a large project where exactly that is. And so we don't have any issues then kind of discovering or trying to find out, where that mesh failure is or where that singularity is. Now, one of the things that people always ask us is, hey, what are some examples of things that people, that engineers are doing actively right now in SCIA that are requiring meshing, that are requiring, refinement, and so on and so forth. So these are just a couple of examples of, these are all real projects from our users. And so for first, just some steel tank structures, so agricultural tanks or some other, grain silo tanks that are being used and using meshing. We have curtain wall structures, so this is a really large curtain wall structure. You can see the refinements at kind of the individual spider connections. Industrial structures, this is a large hopper for grain. And so obviously you can see the mesh here on this particular hopper. Concrete buildings, so we're meshing the slabs on concrete buildings, obviously to get the accurate stiffness of a concrete slab. So in this case, we can see on this high-rise building both the meshing in the shear walls and also in the concrete slabs. We have concrete dome structures, and so this is actually a dome structure that is being designed by one of our clients out in Idaho. And then finally, just some other concrete structures, so buried concrete structures, whether they're mat slabs, whether you have pools or wastewater treatment, whether you have some underground things. The above one is actually the housing, the building for one of those indoor skydiving. So it's actually housing a jet engine, which is kind of cool. And so all of this stuff, uses mesh and mesh refinement in real-world projects in SCIA Engineer. So just a quick review to kind of, before I send it back to Bob so we can open up things for question and answer, just a quick review. Obviously, we talked a little bit about the basic mesh setup. in the model, we talked about how we could automatically generate the meshing. We talked about how we could apply local mesh refinement and also automatic mesh refinement based on loads and based on the geometry. And then finally, we talked about some result tools like averaging strips and integration strips, in addition to some tools that allow us to find issues when they arise in our particular model. So I'm going to go ahead and kick it back to Bob, and I think we can have some time for some question and answer.
Okay, thanks, Ben. So we've got, we'll just take a couple questions here. So first question, is it possible to get a trial version of SCIA Engineer?
Yeah, it actually is. So SCIA, the way, one of the ways that we offer just kind of an evaluation to anybody that's interested is just through a trial. So it's possible to just log on to www.scia.net, and there's just a button at the very top for a free tryout, and then you'll just kind of fill out, there's just some information so that we can send you the tryout. It'll be approved by the local salesperson to wherever you are viewing your webinar from. And it'll be a free 30-day tryout. One of the things that we like to do with the tryout, too, is it's a full tryout. So there's no limitations to it. It's a full piece of the software. There's no node limitations or functionality limitations. So you have a full 30 days to kind of play with whatever you'd like to do. And you also have the option to kind of get with a support person to walk you through some of the basics, show you some tutorials, just so you have a better understanding and an idea of how the software works during that trial period.
Okay. Next question, how does SCIA handle nonlinear material analysis?
So it depends on the type of nonlinear material analysis that we're talking about. So SCIA handles both, a nonlinear, obviously nonlinear geometries when it's doing, second order analysis. Those are just based on using some of the second order geometry or second order analysis techniques that are, standard, the Timonchenko, the Picard, the Newton-Raphson methods, both for 1D members and 2D members alike, and creating nonlinear combinations. More specifically, though, we do some nonlinear analysis material-based nonlinear analysis, plastic analysis for ductile materials. So plates of aluminum or steel or cold form steel or other metals. We have a module that allows us to do allows those materials in those slabs in turn to go from elastic to plastic in that sense. For concrete, we have some stuff for cracking, and that's not really nonlinear, but for cracking and stuff like that, and nonlinear analysis and cracking with reinforcement. And so all of those are different ways to take in the nonlinear analysis in those materials.
Can you discuss the releases between mesh nodes of intersecting 2D elements?
Sure. So in that case, what we would do is, as long as you have 2D elements, you can place a hinge. You're not going to place a hinge necessarily or a release between individual mesh elements, remember, because the mesh elements themselves are attributes that are on, they're not, physical structural objects. And so what you would do in that case is that you would place a hinge or a release at the edge of a slab or something, and you could release it for all 6 degrees of freedom, for rotation and deflection. And you could also, you don't have to release it along the entirety of the slab. You could release it, only at the first 10 feet or the last 10 feet or the middle 10 feet, whatever you decide to. In that case, you have full range of motion in that sense.
Okay, next question. Is there an easier way to model flat slab systems with drop panels?
Sure. And so we didn't talk any about drop panels in this particular demonstration, but what we would do for drop panels would be what we call subregions. And so subregions would just be essentially, you'd model the original flat slab, and then in the locations where the columns are connected to the slab where you want to add a drop panel, what you would do is you would place a subregion there. And so a subregion would just be a thickened or thinned portion of the slab. And so let's say we had our same 6-inch slab here, and maybe our drop panel was a full 14 inches or something. We would make a 14-inch drop panel, and then we can actually, if they're the same in most cases, you could just copy that drop panel around to different nodal locations where the columns and the slabs intersect to create your slab with drop panels.
Is there an offset option concerning beam and slab offset?
Yes. So it's not necessarily what we call an offset. It would be an alignment option. And so in that case, you would choose how you want the beam to align in compared to the slab. So you could say a top alignment, bottom alignment, center line, so that the beam and the slab are their analysis lines are aligned. You could also add eccentricity in addition to those alignments, so you can add vertical and horizontal eccentricity to any 1D member. You can also change the alignment of the slab independently, so you could do the same top-bottom alignment and add an eccentricity as well. So you have full control over those types of alignments, both on the 1D members and the slab itself.
Okay. What kinds of dynamic analysis can you perform in SCIA?
So for dynamic analysis, really, you can do anything from a free vibration analysis, which obviously is a very standard type of dynamic analysis. You can do force vibrations in the sense that you could do a harmonic or a harmonic band analysis. We do seismic analysis in a dynamic feature where we're either doing an equivalent lateral force procedure or a full-blown modal response spectrum analysis. We could do a time history analysis with a kind of a forcing function that changes over time. We can also do some dampening. So you can do a general dynamic analysis but add dampeners to your structure. So all those are different types of dynamic analysis that's possible.
Okay, let's go with one more question. Are long-term deflections considered in the analysis of elevated slabs?
So right now there is we have a module for long-term deflections in our Eurocode version of the software for long-term deflections of concrete slabs. Right now that same module doesn't exist in the American version. So there's some different ways that you can still utilize the European kind of long-term deflections to get some results, but not kind of really apply those to the design codes. There's also some ways that you can use what we call property modifiers to modify the crack moment of inertia of a 1D or 2D member to kind of take into account in a little bit more of a rudimentary way some long-term conditions or long-term effects of the slab. But it's certainly something that for both the code and the American market that we are looking to develop.
Okay, thanks, Ben. So as we finish
Thank you,
up,
Bob.
you can download your certificate of completion from the Event Resources section on the left side of the screen. After downloading the certificate, you can enter your name in it and print and save a copy of the PDF. The certificate will be available through the end of today only. A hard copy will not be mailed or emailed to you. If you missed our note at the beginning and you're watching the live webcast with a group on one person's computer, please download the multiple viewer registration form and complete and submit the form to receive credit. We need this information in case you are audited and we are contacted to verify this continuing education activity. Additionally, this webcast has been recorded and will be archived on csengineermag.com/continuing education. For viewers of archived webcasts, click on the quiz button at the bottom of your screen to take a quiz on the presentation. Archived viewers must pass a quiz in order to download a certificate of completion. The answers to all of the questions submitted today, even those that we didn't take time to answer, will be available online within a few days at csengineermag.com/continuing education. So please check there for further discussion about today's topic. As we conclude, you should see a webcast evaluation survey. We appreciate your feedback, which helps the WAY Group and sponsors such as SCIA plan future webcasts. So thank you to Ben Follett and to everyone who joined us. This ends today's webcast.